now moving on to yourself actually, EasyPCB. So Project Origin for this one, UPCS Hackathon this year, I believe you guys won the hardware?
Yeah.
Or something like that.
Interdisciplinary.
Interdisciplinary, yeah. Very good. If you'd like to put, these on,
yeah,
you're welcome to. Fancy. And then that's the mic so everyone else can hear.
Yeah.
And your slides should be, they should be on here. If they're busted, then I'm very sorry.
Awesome. Good evening, everyone. My name is Matt. This is Zach. We're going to present to you EasyPCB, which we did 3 weeks ago at the UPCS Hackathon. Probably want to manage expectations a little bit. This is like a 24-hour project. It's not a thesis, but we think the idea is pretty cool. So we're just going to try and explain it to you as best as we can, and then if you have questions, feel free to shoot. So basically, for all those unaware, this is a printed circuit board, a PCB, and it's a bunch of fiberglass and copper, and its job is to make electrical connections. And so if you're just software, this is eventually what your code actually runs on-ish. Not exactly, but they're everywhere. They're in pretty much every piece of electronics. There's probably hundreds in this room. They're really, really important. But they're also really hard to design. So, I know you can't really see this, but basically there's a bunch of little copper traces, and they all have to connect different things on the board. And so when you're designing it, you have to connect those traces. But then as you lay traces, you block other traces, because if you connect them across each other, they're connected, and you just connected your wires together. So it doesn't work. So what ends up being is a pretty tedious process, and there's a couple of tools that have been invented to try and speed this up, because on large designs this can be weeks of engineering time. Like it's a real pain. So auto routers exist, where you put all the components on the board, and it will try and connect them. They're not good. The one we made isn't good either. But we sort of took it a step further, and we tried to do the placing as well. And instead of just trying to solving it means different things depending on what you want to do. So if you're cool with having a massive board, then we can make a massive board, and it's going to be pretty easy to do. But if you need a really constrained board, well then we want to account for that as well. And so the idea is you have like 3, 4 different sliders, and you tune what's important to you in your design. So the ones we went with is board size, how components are spaced, the via count, as well as just general clearance around the rack. So it gets a little bit technical, but they're all things that you want to tune depending on your design. And we just want to make it super abstract, super easy. You tune the sliders, and that allows us to wrap the board based on your preferences. I'll probably hand over to Zach a bit, and he can tell you how we tried to do it.
Cool. All right, so this is a diagram of like a circuit schematic. So this is how you start your design process. So this is an example of a MOSFET driver for an LED. It's a pretty basic one. It was just something that's complex enough to prove that it works. Like a kind of a non-trivial example. So this is basically just showing all the components that you want to lay out on your PCB, and it shows how they're connected together. So in the software, you go through and you design this, and it basically then exports a list of all the components, properties of those components, like where the pads are, and a net list showing how all the pads will connect together. Then what happens is you convert it over to a PCB, and the software automatically places it in virtually a random position. It's then your job to go from this random thing, first place them in a less random position, and then connect all the nets. So this is the first step of what our program did. This is the somewhat optimized placement. So all these blue purple lines, those show where copper needs to go. So ideally you try to minimize the length of them, and you try to minimize how many times they cross over. Because every time it crosses over, it becomes harder for you to route. So what our program did is it went through basically all the combinations. It was a slow program. It went through a lot of combinations to try to work out how it can minimize trace length by trying to force, like using a force model to position them, and then adjust the orientation of the components such that we can try to minimize how many trace crossovers there are. And it's done an okay job here. So it's a lot better than what it started out. Of course, this is a very simple example, and when you get a much more complicated PCB, like these become massive. One of the other things is PCBs aren't just one layer. They are almost always more than one layer. This one is 2 layers. The one that's being passed around is 2 layers as well. They can go up to like 24 layers. So for something like your motherboard in a computer, the CPU has an incredibly dense pin pitch. And so you need to use multiple layers. So not only are we about to try to solve a maze, we have to solve a maze in 3D. And as we're solving the maze, we're also making it more complicated for ourselves. And so this is the result of what happened. So it basically ran an A-star algorithm. It was a very modified one, where it would try to route a trace, it would pick a random net, try to route a trace, and if it runs into a block, it tries to make its way around, unless there is a shorter path going down onto the bottom layer and then popping back to the top. Yeah, that bit also didn't work too well either. So, in terms of other things we have to optimize, we were talking about, like, you want to optimize how well, like, you might have size constraints, and so your PCB needs to be a certain size. Often though, you want to try to minimize trace length, and you want to minimize the number of vias. So these like grey circles, they're called vias, and they're what happens when you need to take a copper layer from the top down to the bottom. And the exact reasons why you want to minimize them becomes a bit complicated. But for a circuit like this, it's a MOSFET driver for an LED. And let's say you want to, PWM or like control the brightness. You need to be switching it on and off pretty quickly. And when you do that, even if you're switching it at a low frequency, the edges of your voltage transitions are very sharp. And because of the Fourier series of square waves, you end up with really high frequency components of those voltage signals. And because of the black magic that is RF electronics, all the wires don't just become wires, they become inductors. And whenever you have a big pad like this, it doesn't just become a pad of copper, it becomes a capacitor. And so whenever you have these vias as well, it just does really bizarre things to your voltages when you're trying to either switch really quickly or switch at high frequencies. And so we're trying to minimize the number of vias. And so even manually designing a PCB is really difficult to do these designs properly. It's very hard to simulate these effects. And so you just try to minimize the results of this in the design process. Cool. And this is the result of what comes out. So this is like a 3D render of the PCB. And yeah, it ran pretty fast actually. So if I were to design a PCB like this, it probably would take me about half an hour to route something like that. It took our program 2 or 3 seconds. So there are significant time savings. Our approach isn't very scalable though. The Oliver factorial really slowed it down. The multiple Oliver factorial. That slows it down a bit on larger designs, but it's a cool proof of concept.
Yeah. So we're not really claiming that we implemented this particularly well. But what we probably will say is, from what we can tell, no one has tried to do the auto placing first. Though they'll just auto route will go, here's all the things, and I'll try and connect them, and if I can't, then I'll just die. And the routing is very, very difficult to place. If you organize things properly, it makes it way easier to route. So the idea, I think, is quite interesting. It actually probably has a bit of potential for someone who already has software like LTM to implement. Because auto placing first would genuinely speed things up a lot. And then you can actually have good auto routers, which would be really, really nice. But yeah, other than that, that's pretty much what we did in a weekend. Have we field any questions if anyone has any?
What are like your next steps from here? Will you try and like optimize that further factorial, or will you try to port it to more like PCB places like RT and stuff?
It works with LT in
Oh.
theory.
Yeah. So what we do is we just extract the file that contains the netlist. We know what needs to be connected to what. We run our program, and then it turns it into an importable file back into basically any PCB software. So compatibility is not really an issue. N factorial is for the rotation algorithm. Basically just check all of the permutations or rotations of all of the components and see which one has the least crossover. There's definitely more intelligent ways to do that. Yeah.
I don't think that's the biggest issue though, either.
No.
Sure, it eventually finds. Like, even if it's open factorial, whatever, that fine, whatever. Let it run forever. Our approach for the maze solving of like trying to actually run the traces just wasn't very good. The implementation was very poor, and that was my fault. But I think just a better method of routing and better optimizing when it changes layers is definitely, like, first it should work and then we can optimize the elephant factorial. I think.
Like, would you try to sell like? I know it's like a hackathon project, but do you have plans to like make it better and hopefully sell it, or like turn it into a business, or do you like intend on like keeping it like as it was?
I'd like to keep on working on it eventually.
It'd be cool if it worked. Yeah, to be honest with you, we haven't really discussed it since we made it. We haven't really looked at the slides or thought about it since we made it. But yeah, we do see a little bit of potential in it. So once sort of getting fried by uni, it could be cool to spend a bit more time on it and see where we can take it. Okay. Do you have a question next?
My question got answered. I was going to say, how do you import it?
Yeah.
That was exactly what I was asking.
I don't remember the specific file types. I'll go.
Everything was remarkably standardized, considering that, there's like 20 different PCB design and schematic design softwares. It's a file type from the 80s or 90s or something, and nobody's been bothered to change it because it kind of just works. And so there's no interpreters for it, but we managed to reverse engineer these file types in the weekend.
That's pretty good.
It was remarkably straightforward. Just set file types. What was that? DSN and SES or something like that. It was because you export it in a different file type as what you re-import it. So
Very good.
Well, one last question. How does sliders work at the start? Is it like some function you're trying to optimize based on those sliders position?
Yeah. So for instance, for the board size,
Yeah.
there was a few different approaches, but if you saw how everything was connected with straight lines, what we do for the placement is essentially model the lines as a force connecting a bunch of elements in space. So the slider just tunes how strong that force is.
Right.
So it could be repulsive and really try to shove everything out of the way or crush it in.
Yeah.
Stuff like the V account, that is handled in the maze solving algorithm. So there's a certain cost for going between layers. And that slider basically tunes what that cost is.
Yeah.
So that's really hard. It's like, try to do everything it can to not see layers. Otherwise it'll just do a little bit. So stuff like that, just try to keep it really abstract. Cool.
Very good.
Thank you for listening, guys.
Thank you.